I'm from Seoul National University and I'm teaching environmental engineering since 1995. The topic of my presentation is the removal of heavy metals using tire-dried activated carbon, or TAC. And my lab is Geotechnical and Geo-Environmental Engineering in the Department of Civil and Environmental Engineering. Next. Okay, let me start the introduction. Next. Okay, the main idea of my research is to, for example, we have industrial area or facility like factory. There is still is likely to have a lot of contamination from the factory, like leaking of some contaminants from the industrial zones. Then it can contaminate the soils or even groundwater zones, which can be the good resources for drinking water. So we'd like to try to reduce and prohibit this spread of the contaminants for soil and groundwater. This is the main idea of my research. When I look at the contaminants, the contaminant can be classified mainly two different categories. They are heavy metals, like this, and also the organic compounds like phenols and PCBs and all those organic compounds. But today I'm just talking about the heavy metals, like inorganic compounds. In the data from the 2009 from the Ministry of Environment of Korea, there are all different types of heavy metals. The main thing are zinc, lead, and copper. They are the main parts of the contaminants. And I'm targeting those heavy metals for the industrial use. So next, for example, when we have rains, and when we measure the pH of the rains, these days we have like acid rains. So the pH of the rain is like between 4 and 5, which is quite acidic. It's not like neutral, like 7, 8, not like that. So these types of low pH rain could leach the heavy metals, easily moving in the subsurface zones, so that they can, drive the spreading of the heavy metals quite easily in the subsurface. So next. Okay, so I try to reduce of the spreading of the heavy metals in two different ways. For example, like for soil zones, I try to add some additive materials, mixed with the soils, and then I try to stop or reduce the spreading of the contaminants, like heavy metals, before they become like this one, like spreading. And this is for soil layer, and this is for the groundwater. I can set up some permeable filter layer in the groundwater zone. Then when we have some contaminations, then these contaminants can pass through this permeable layer or filters, and then they will be, reduced. The contaminant level can be reduced. This is called permeable reactive barriers. So there will be two, different ways. So my target for research is to develop some material for PRB and also for the soil zones, like a mixture of soil and these materials. Next. And there could be a lot of different types of materials, like activated carbons. This is very, very general, very commercial, and we use them in many ways to reduce the heavy metal and also the organic compound. And zero-valent ions, like a small powder of ions. They can do some reductive dehalogenations so that they can reduce halogenated hydrocarbons very well, very easily. And also the zeolite. These are the pretty common materials these days we are using. Zeolite is very good for cation exchange capacity, so they can easily catch the heavy metals very easily in the subsurface. These are very general. So what I'm doing is I try to develop some good material like these types of capacity, and then also they should be somewhat inexpensive. These are somewhat expensive materials, so I try to use some renewable materials or like reusable materials to reduce the cost of the compound. Next. So the ideal material should exhibit good sorption capacities. My mechanism here is sorption, catch the contaminant and hold them for a while in the subsurface and comparable to commercial product like this, while being they are cost effective. Next. So I look for all different types of materials, and I'm focusing on the waste tires. There are a lot of waste tires. For example, over 3 billion tires have been reported discarded worldwide each year, a huge number. Over 10 billion tires stockpiled in landfill. In case of South Korea, for instance, the annual rate of scrap tire generation is about 20 million numbers of waste tires like this one. No sufficient landfill for disposal of waste tires in South Korea. Our country is a small-sized country and heavily populated, like 50 million people. So there's not much area for landfilling like this one. So we need to, try to find some way to, reuse these materials, these good materials. In the waste management in Korea, about 80% is to recycle, which is still very high. And about 10% is landfilling. And another 10% is like incineration. So they have the main composition of the waste treatment in Korea. But 80% is still very high. We try to increase 1 or 2% for recycling, but it's very difficult. We are almost saturated, 80%. And landfilling, as you know, we have limitations with small country. And incineration, which is good. As far as I know, in Japan, incineration percentage is much higher than Korea. But in Korea, incineration, we know that it's quite effective way because we can reduce the volume of the waste very, very much, like 1/20 of the original volume, which is good. But in Korea, even, for example, each local government has a very good incineration facilities. We cannot use it effectively because people, like neighbor people, local people, they don't like it. When we incinerate the waste, then we have a lot of dust coming out from the facilities, and also some smoke out from the incineration facilities, and they really hate to see such incineration activities. So it's quite limited. So the one way I focus is to reuse the waste tires. Therefore, the proper management of waste tires for recycling has been a major environmental concern. Next. For the waste tires, these days, about 10% we can use the waste tires as an energy source. And about almost 50% we can extract some effective, good sources of petroleum hydrocarbons, and just about the 40% is like a char processing. So the char has carbon which can be a suitable source for making activated carbon. So I focus, char processes. Next. The main objective of this research is making activated carbon from waste tires. The tire activated carbon efficiency for removing most common heavy metals in South Korea, lead, copper, and zinc, in comparison to commercial. So I compare the new material, new renewable material with the commercial activated carbon, the efficiencies, and also investigation the geotechnical properties as absorptive film materials. I try to mix those materials with the local soil. Then it has a good engineering property as a foundation bearing materials, because we have to build some industrial facilities above the soil zones so that it should have a good bearing capacity against settlement and also against some shearing strengths. So even though when we mix with the tire material, it should show some good engineering capacity against the some settlement as well as the absorptive capacity. Next. The pyrolysis procedure for the waste tires. Firstly, I try to pulverize the waste tires, shred them, and then we put it into a small oven temperature, and I increase the temperature up to like 550 centigrade Celsius. Flowing nitrogen gas while heating is like a char processing. So, and then I get the tire char. Then I activate the tire char by potassium hydrocarbon so that we can clean up all those surfaces and activating the surface to have a good capacity for absorption against the heavy metals. And then again, I hit the TC, making the activated carbon and washing TAC with 1 mole of hydrochloric acid for removing any hazardous product. And then finally, I have TAC as absorptive materials. So after I making those TAC materials, I compare the capacity against the heavy metal absorption with commercial activated carbon. Which one is good? Then this is the general process. I adapt the batch absorption test for based on the US EPA methodologies, which is like in a small vial. I put the TAC or CAC and add some solution of heavy metals and shake it for a certain period of time, and then filtration, and then I check the concentration for the liquid. Then I can understand how much soak onto the materials, new materials or commercial activated carbons, and I compare the CAC and TAC, which is good. Next. And also, I'm also interested in the reusing of those materials. As I said, I can mix it and install it in the filter material for the groundwater, also for the soil layers, and I'd like to use them again. So is it possible to reuse them? TACs. So I check the batch desorption test. After sorbing the material with the heavy metals, I try to wash them and leach all those heavy metals and try to use create as a new material. So after drying samples, mixing with 50 milliliter of solution of hydrochloric acid and shaking for 24 hours and measure the dissolved concentration. Next. Then I also try to understand what is the main mechanism of absorption. Catching those heavy metals by TAC or CAC, and I compare. Next. Then I will find out this is for lead, copper, and zinc, and red dot is for the commercial activated carbon that we can buy. And TAC is from tires, and I found out that the capacity for TAC is quite impressive. They are even like 8 times higher than
the red dots, which means these guys, TAC, the tire activated carbon, can catch almost 8 times higher amount of heavy metals than the commercial activated carbon. And I tried to find out why. I'm going to quickly explain why. The the experiment, the heavy metal sorption capacity of TAC is much more than CAC, almost approximately 8 times higher than CAC, which is very promising to me. But I tried to find out why they are very good, showing good capacity than the commercial activated carbon. Next. And actually, these all numbers are the graph that I showed you before the previous pages, 8 times higher than CAC. And absorption sequence of examining the heavy metals was like the lead was very wet, so onto the TAC, then copper, and lastly zinc. The logical justification for this result is the smaller hydrated radius of lead ion compared to copper and zinc. So lead ion is entering easier inside the porous medium. Next. And this is, renewable capacity. What I'm saying is, can I use those material again after washing, and then can I use them? This shows, like with the pH 2, which is like hydrochloric acid, I can wash them easily. So this is the amount washed out by for TAC, and this is CAC, just like the graph that I showed you before for absorption test. So I can say that from this graph that, oh, yeah, sure, I can use them again. But in practical application, it's really difficult. Once we install on the ground, then it's really difficult to get them out and wash. I think that's not a good idea. It costs a lot. So, but logically it's possible. But I don't think we really do reuse it in the application in practice. So, but this is just showing the possibility of reusing the material. Next. So the released metals, like a pH value like this is very strong acidic condition, neutral, basic condition. This is like a acid rain condition, and I see that this is the maximum contaminant level, like the EPA, environmental contamination levels. And for this, if you look at this number for zinc, this is much higher than this one, right? But in the natural condition, we never see pH 1.5 in nature. In nature, this is just possibility to detach and washing. So normally we just focus on this, and we see that all these numbers are much smaller than this one. So I think we can safely use them in nature. In application in the field. Next. And I focus on why TAC shows much higher sorption capacity than CAC. And for CAC, commercial activated carbon, they show the curve like this one, sorption and desorption, curve like this. And this is, by the IUPAC categories, sorption mechanism, it's like this is type 1 classification, which means absorption is mainly in micropores and on the surface like this, monolayer filling. So that's it. For CAC, this CAC shows this curve for sorption and desorption, and this is categorized by the IUPAC classification system that this is micropore filling and monolayer filling, like this. So the capacity is quite limited. But, next page. For TAC, it shows quite different curve like this type. This is categorized type 4 by IUPAC system. This means not just the surface, but also all those pores inside the solid particles. It's all filled like this. So that's why it absorbs much more heavy metals than the CACs. So this is, I mean, the sorption capacity. That's the reason I presume that the sorption capacity for TAC is much higher than the CAC. CAC just shows the mono leg of, sorption, but this one, TAC, higher activated carbon, shows filling all those, the surface. And I want to see what the surface really looks like. And for the next page, this is the size distribution of the material, and it shows mostly, this is size of the particles. This shows mostly one size, single size of pores, but TAC shows all different distribution, different sizes. Which one? Some particles are big size, some particles are small size, so that it can fill all those pores. So we can create a lot of, different surface areas too. Next. And this is TAC, and this is commercial activated carbon. And it looks like this is quite, a smooth surface, and no, surface tortuosity and the roughness. And this is TAC surface, and I see that the surface is really different, and I see so many pores, and there is no, pores that the heavy metal can get into. And here, there are so many pores by SEM microscope that I see so many pores so that the heavy metal can travel and soak on the small pores in the TAC. Next. And next, I just quickly check the geotechnical properties. When I mix TAC with the local soil for industrial facility site, then the soil must maintain and retain the heavy load of the building. What I'm saying is it must show good shear strength, and it must show the good bearing capacities. So I check the geotechnical properties. Next. And this is a compaction test result. And next, maybe this is good. This shows even though I mix with the soil and TAC tires, it shows a very good capacity for the bearing capacity. So I can say that I can safely mix the TAC material with local soil, and it still shows good bearing capacity against the heavy load of the industrial facilities. So I checked the sorption capacity and also the bearing capacity of soil, the mixture of the sorption TAC. Next. So I checked, I tried to compare all the different mixtures, like 10% mixture, 20% mixture, 30% of TAC, 40%. I keep increase the mixture ratio, and I found out this is very important. Friction angle. Friction means like a friction between each particles, and it shows still very high. If it is like more than 30, like this is too small. Like more than 30, this is like sand. Sand has a very good friction, angles. So I can say that even I mix with almost 25% of tires, still shows pretty good, engineering capacity. So I don't worry, even though I mix tire with soil, good capacity for bearing against the settlement of the facilities. Next. And this is just the conclusion. Sorption capacity of TAC shows much more than CAC, and desorption efficiency of both TAC and CAC were high enough for reusing them in permeable reactive barriers, but I still doubt that I really reuse them in the field. But this just shows some possibility of reusing them. TAC had a higher pore volume than CAC. That's maybe why TAC shows higher sorption capacity. According to IUPAC classification system, TAC has a mesoporous characteristics, while CAC shows microscopic characteristics, microporous properties, which means the sorption by TAC is occurring in multi-layer, while it's taking place in monolayer for CAC. Mixing of soil tire can be used as sorptive fill material in the engineering application. What I'm saying is geotechnical property of the mixture is still good. What I'm saying is even up to 25% of mixtures, it's okay, still good. But actually, this is just for, academia, but I look at the possibility of reusing the waste tires. But as you see, to create TAC materials cost a lot. What I'm saying is, I use the pyrolysis, like using the high heat of almost 700 degrees Celsius. It costs a lot, right? And also I need to pulverize them. Another process costs another, big amount. So this is up to here is just looking at the possibility of using waste tires. But in the future, maybe I think we can use them in a more effective way. What I'm saying is cost less. Right? That's it for now.